Good evening and welcome to the stream tonight. Hope everybody's having a great night so far. It's been a few days, maybe a little over a week. I guess I could have checked that before I started, led off that way, but yeah, it's been a busy week this past week, so just haven't quite gotten around to streaming as much. Lots going on, and hey, we just transitioned my kid from 2 naps a day to 1 nap a day, which is great, but also tiring. She handled it really well though, so last couple days have been going more smoothly. But anyway, yeah, I'm excited to get back into Space Engineers. Yeah, it's been a week or so since I streamed, but it's been even a little longer than that since I streamed this. Been doing some work offline, but honestly, I haven't found a lot of time to do that. But I figured I could show off some of what I did to kind of get things started. Um, Actually, yeah, let's do that. We will switch over to Visual Studio. So let's see. I made a note of some of the things I changed. First, a couple of these things were pretty simple stuff. It was mostly stuff that made testing my code easier. You know, rerunning new things as frequently as I've had to. Um, it's valuable to be able to streamline that a little bit. Um, so one thing that I noted, well, so this didn't have so much to do with streamlining the testing, but just making the code itself more efficient. We were calling the heuristic function a lot on an individual state, um, calling it several times, mostly because it was used in the logging output up here. Um, and as the algorithm's gotten more and more complex. Oh, I should probably mention that. Yeah, for anybody who maybe hasn't been watching, if this is your first time catching a Sentinel stream, yeah, maybe I should let you know what I'm doing. So Sentinel is the name I've given to this project where I'm working in space engineers to create AI. um, the wonderful long-term goal is a very broad AI that can basically, the goal is to have it like control its own faction of ships within the game that can operate on their own in survival mode. Sounds really fun. Right now, we're just trying to fly the ship. Um, and right now, we're just flying a ship with, you know, basic thrusters in every direction and no gyroscopes. And yeah, it's very simple, but, it's setting good groundwork. Um, and yeah, I'm doing all of this using the in-game scripts in the programmable blocks, um, to 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 do this in a way that, I mean, can be done with, I don't know. There may be mods and stuff that can do this kind of stuff in a maybe more elegant fashion, but I'm setting this up in vanilla Space Engineers. But anyway, yeah. So right now, working in this A-star algorithm that's supposed to evaluate all of the possible ways I could fire my thrusters, um, at any time, and it works out the most efficient combination of thrusters to get the ship from where it is to where I want it to be. Um, and so yes, the heuristic function is that guess as to how much time it will take to get from wherever it is in the state that's passed in, to the goal. Um, and yeah, as this algorithm's gotten more and more complex, this function has gotten more and more computationally intensive. Um, and yeah, so the fact that I was calling it several times and partially just for the sake of logging, um, was really not not great for the runtime of the algorithm, which is particularly relevant when I'm trying to run it in the in-game scripts that have a cap on how much you can do in a single tick. We can spread this execution across multiple game ticks, but still, the fewer it takes, the better. But anyway, I modified my usage so that we just call it once when we create the new state and we store it in the node. So I'm going to mute for a second so I can sneeze. All right. Anyway, so yeah, so we'll compute it once, and we can then store the value in the node class, and then that gets reused later on, like in the logging. We can just reference the node h score instead of calling that expensive heuristic function again. Anyway, that was relatively easy. It's fine. These were the little cleanup things I wanted to do offline anyway. I set up a single variable in the overall in the top level script class to be able to switch back and forth from the normal execution where it would just try and do everything tick after tick after tick, and switch it back to the step by step execution where I could be looking at the programmable block and say, okay, check the next node, look at the logging. All right, check the next node, look at that logging, and so on and so forth, and kind of force it to go step by step. And I realized I was making like 2 or 3 different code changes every time I wanted to do that. Swap back and forth, and it's much easier to just put a flag at the top of the class that's easy to find even in game. It just shows up right at the very top of the script, so easy to switch. I had noticed, you might remember if you were watching last time that there were cases where we would evaluate states where like the forward thruster had fired, moving us forward a certain distance, and then there was another state where the forward thruster fires, the right thruster fires, and the left thruster fires all together. And logically, I know that gets us to the same place because the right and left thrusters cancel each other out. But every once in a while, you could see, when I'm checking the details of exactly what values are showing up, I'd see that some of them had different values calculated, and so I did a bit of time stepping through stuff just to basically to confirm that that is just caused by rounding error. Unfortunately, the computer can only store so many decimal places in order to do its math. So when you do a lot of, especially multiplication or division with floating point numbers, they end up getting off by a little bit. And so it seems like that's just caused by rounding error thing. So that was nice to see. And I do have, let's see, which oh, there it is. Yeah, I knew I had a constant defined somewhere in the A star. So I had already put in some restrictions to rounding some of those numbers because I know there's rounding error. You want to compare floating point numbers on a computer, and there's a chance of rounding error. You have to compare them within a certain range, just because there's very little chance that they're ever going to end up actually equal. And I think I had originally set this to like 6 or 8 decimal places, and turns out that's not quite enough. So I dropped it back even further. And really, 4 decimal places of accuracy, like that's talking about 1/10,000th of a meter. All right. A tenth of a millimeter. I don't know how you're even going to see a tenth of a millimeter in game in Space Engineers. So, um, like it's barely relevant when you actually think about it like that. As much as it'd be nice to be as specific as possible, um, this is plenty accurate enough, or it should be. Um, but yeah, so that was relatively easy. Once I kind of confirmed that was what the problems we were having, I kind of dropped this back, and I had more successful runs with uh, test runs of the algorithm. Still not getting like perfect execution every time, um, but it's better. It's definitely better. Um, so there's still room for improvement, and I have a couple ideas on how I want to do that. So that's some of what I want to work on tonight. Um, but that definitely helped. And so the last thing I ended up doing that's I actually thought about streaming this, and then there's a whole story, I guess. What I'll describe first what I did. What I decided I wanted to do was, it's kind of a lot to, and I've talked about this when I've been testing it, like it's kind of a lot to go in, export the script, there it is, deploy the script, go into the game, import it into my template ship, save the template blueprints um, to the template ship, and then add that to the projector block, and then rebuild a new ship, and yada yada yada. I guess I don't always have to do that. Sometimes it's just importing it into the ship I'm testing with, but even that, like, it takes a long time. It takes enough time that it adds up when it's done repetitively. And then when I'm testing, I have to rely on the output of the what the programmable script can provide, and I have to be looking at that block as it's running in order to see any of the output. And it's only got so much space, and I can't step through the code without bringing in a third-party application to decompile it and set up breakpoints that way, which is a whole other pain. Um, what'd be much nicer is if I could just execute this code in Visual Studio, but Visual Studio isn't aware of the Space Engineer's world and what the ship is and where the ship is and all that. So what I wanted to do was basically create a mock framework so I can say, hey, I know you don't actually, you may not have access to the actual game, like what's expected when I'm setting up this script, but I could tell it, okay, I'm going to tell you, I'm going to I'm going to give you a mock implementation of a ship controller, and uh, these are the values you need to know about. Um, which in our case, in the case of our algorithm, the only thing it needs to know about the ship controller is the mass of the ship. So I went into the space engineer's world that I'm in, and I had the ship spit out its mass and set up in my test class, say, hey, just set up this mock class, pretend there's a controller there, and pretend it has a mass of 2,600 kilograms. Um, so that as far as this code knows, it's in game and it's asking a real controller what the mass of the ship is, and the controller says it's 2,608 point whatever I just 0.8 kilograms. Say, great, I can work with that. And similarly, I did the same thing with the thrusters. The thrusters were a little weirder because I had to account for the world matrix that tells that is the game's way of describing where in space the block is and what direction it's oriented and all that. Um, but again, I just had the ship spit out that data and I copied it into here. Um, yeah, it's great. Gave it a name, showed the orientation within the grid, and the maximum thrust. Um, and then I can basically just run the algorithm completely within Visual Studio simulating the Space Engineers world. It's a simulation within a simulation. Space Engineers, the game, is already, pretending to be real life to some extent. Yeah, now I'm in Visual Studio pretending to be Space Engineers. So yeah, it's actually kind of cool. I'll show off a couple of these real quick just because they're kind of neat. So wrapping the whole thing. So we have our script is contained in this program class that inherits from my grid program. And my grid program has a couple key functions that we need access to. So I created a mock program that can inherit from our custom program. And ideally, this framework can actually be shared between any scripts that I create. Since this is the only project I have right now, I haven't really played around with what the best way is to make it shared between different projects when that comes up. But when that comes up, I'll figure it out then. But yeah, but all of them will always be called program, just because that's what the script class is supposed to be called. So we have this mock program, and because our script accesses the runtime, the echo command, and the IGC, the integrated communication system. Oh, I don't actually need these anymore. I set up mock ones, pretend ones. And this is the kind of thing I've done at work when we're testing, when we want to write unit tests for our own code that rely on some third-party thing functioning. Instead of actually relying on that third-party thing functioning for the purposes of our test, we'll just write up a mock for it, be like, all right, I know normally you need to ask this other thing for information, but for the sake of our test, just pretend it gives you back this, this much more, this specific thing that works for our case. We don't have to rely on whatever else functioning for our tests to work. And so in this case, I don't have to rely on the game running for our tests to work. So yeah, I created a custom grid program runtime info that controls things like the maximum number of instructions that you're allowed to execute in a single game tick and how many you've done so far. There's also a stack depth limit, chain depth limit, and the update frequency of the programmable block. But for testing, I'm not actually limited to how many instructions I execute in one go. So I just say, hey, execute, I can go int max value. It doesn't really matter what I put here because I always put current instruction count to 0. I don't have to keep track of it because I am not actually limited when I'm running in this environment. Normally the game's implementation of this does track that, but for the purposes of our tests, it doesn't matter. So whenever in the A* class, here in the, is it here in run? Yeah, here in the run function, we check how many instructions we ran in our last loop and how close we're getting to the maximum number of instructions we're allowed to execute. But because I'm using my custom values, this is always going to say, oh hey, yeah, this is huge and this is 0, so yeah, no, you're not anywhere close, keep going, you're fine. And it just keeps on rolling through. Works great. Similarly, wait, not this one. Where'd it go? Mock program. There we are. I can get rid of that. We also call echo a lot to log, and normally the echo prints out to the programmable blocks. Here up in my Space Engineers window, it'll print out, to this space down here when it runs. I have something in here, right? Oh, maybe. What is in here? Oh, this was my thing to find the controller and thruster information. Why aren't you running? Oh, no, I know why. Because I told it to print out custom data. Yeah, so the test script I have in here right now isn't actually using the echo function, but normally the echo function would print something out here. And so instead, I want it to print it out to my console in Visual Studio. So I just changed echo to console write line. And then the intergrid communication system is used for this ship communicating back and forth with the brain script, which, again, for the purposes of my tests, I'm not actually using. But because I did initialize it in here, I did put a mock one together that basically just does nothing. It allows me to call the methods that I wanted to call. It can, get and create a new listener that does nothing. Because there's no actual communication going on in here, this whole thing basically just does nothing. But it's there and it allows the code to run. And then I showed you a little bit of the ship controller that has the mass, and the blocks. So the ship controller and the thruster both inherit from. I thought ship controller inherited from a functional block too. I guess not. Weird. Anyway, sorry. They both have, like, in-game a whole host of different interfaces they inherit from. So the functional block, the terminal block, the cube block, and the entity, which is basically like the entity represents any object in the game. It can be the blocks, it can be floating ammunition canisters, I believe the players, probably even like floating ores, things like that, I believe are all entities. And so they have certain qualities, like names and IDs and world matrices representing their position and orientation in the game. And those are common to everything. And then all of the actual blocks inherit from cube blocks that have other things like their, mass and where they are in the grid, since the blocks are all considered to be in some kind of grid, even if they were alone. And this is common to all the blocks. And the terminal blocks are what? Why are the? Oh, I guess the terminal blocks are the ones that will show up in this list. And so they've got their own properties, some extra info, things that can, whether they show up in these various screens. I didn't actually have to do anything with this, I don't think. And then the functional block are blocks that can be turned on and off, like thrusters. And apparently not controllers. It's weird. Yeah, so like thrusters you can turn on and off. The remote control you can't. Yeah, that's weird. I would have thought you could. But yeah, you can see, like, in game here. Actually, I might need to swap these so you can see it a little better. Let me flip the picture-in-picture there. And I'll go back to the terminal block. So you can see where these toggles are. The show in inventory is this, or show in terminal is this. Show on HUD is here. Yeah, got all these common properties there. And so like for my thrusters, so I have mock implementations of all these too. And they, I didn't implement everything. Right now I'm not using the enabled value, so I'm just ignoring it. I'm not going to mess with implementing it because I don't need it, and it throws these exceptions. So if I try to use this framework in the future, I'll have that reminder that, hey, I didn't actually try to do anything with this, so it's definitely not working. because if I try to implement something now, I might not do it in a useful way. So I'd rather just save it for when I need it. Like the terminal block uses a bunch of stuff. Oh wait, no, actually, I guess we don't have anything specific to the terminal block. I'm passing everything through. The cube block, we care about the display name text that gets used in some of my logging. And then at the entity level, we care about the world matrix. So yeah, but again, that's all I implemented. All these other things, my script never touches, so I just left them alone. But yeah, it's kind of cool. And this part all actually came together relatively easily. So yeah, originally I was thinking, yeah, maybe I stream this part, you know, writing these mock interfaces, and then the night that I finally got around to working on it, I'm like, didn't really feel up for streaming that night. But I was up for working on this, so I figured it wasn't super exciting. I didn't feel bad about doing it off stream, but the awkward part was once I actually got them written, because writing these classes was fairly easy, but I had some little things that weren't quite right that actually took me a couple hours to debug through, and I'm really glad I wasn't streaming for that, because that would have been boring as hell to watch. So in the end, you know, I think it worked out all right. I think it worked out for the best. And yeah, ultimately, it allows me to set up these tests, and I've had this test running for a while, and I'm going to kill it because clearly it's not working. Like I said, not every setup is working quite right at this point. I did set this up because I wanted to see. What I did find, so I'll do this a simple way. Right now I've just got this looping through to call this, and I'm just doing much like I have had, you know, at the top of my script, where I'm looking at, you know, how far forward, up, and right from the ship do I want the goal to be that I'm searching for. And so yeah, I'm doing the same kind of thing here, where I'm setting up the goal forward, up, and right. And so, you know, right now I'm just testing. I wanted to see, you know, hey, if I loop through everything at every distance, which ones work and which ones don't. And I don't quite have it perfect, but I can show off like running this, because this will only run at I equals 8. I know this one works. Takes a second, but it takes a lot less time than exporting this and loading it into the ship. See there, it's done. And here's my output down below. Wait, I'm on Visual Studio Focus. Good. I'll just pull this up so you can see my print output here. I removed a lot of the extra logging about the specific nodes because I don't need it if I'm coming in this way. But yeah, prints out the instructions. You know, thrust forward a bunch of times, and then thrust backwards to start braking. And because I'm giving it a large amount of leeway, excuse me, to be determined, you know, when it's reached the goal. I think I've given it 3 meters in this case. Yeah, it doesn't have to brake for the same amount of time as it accelerates. Once it's done, once it is done braking, it will come to a stop. But yeah, and this is basically what we've seen happen in the game before. And I should actually try. I'm back to time step ticks 10. Oh, I think it worked better with 1. Oh, maybe that's why that was failing. Okay. Sorry, I'll come back to that in a second too. I want to show this off because it's cool. This should be fine. That's all the same. So yeah, let's deploy this script. I will flip back to game focus. Let's see. Remind me, where are we? Okay. So get rid of this ship. That's fine. Don't need it. import the script into my template ship. And we copy the template ship, replace our blueprint with the clipboard. Head over here, projector, blueprints, replace with the latest ship. And then we say, yeah, that one. Fun. And so now it does our thing. We'll build the ship. Drops out. The arm drops away. Then the ship is instructed to calculate its route. And then... oh no. Well, that's embarrassing. I thought that was gonna work. Whoops. Hold up. Oh, it did. It found a solution. Oh, do I need to update my brain, class? Yeah, do I need to update my brain? Oh, don't you hate it when you need to update your brain? I didn't think I'd changed anything in here. Alright, actually, let me just watch the brain logs here. I am going to recompile the brain script real quick because it probably when it doesn't finish completely it fails. But yeah, you can see here is where the logs show up as I was talking about. So we got an acknowledgement from the welder that's building, releasing the ship. Registering ships. It never got acknowledgement from the ship that the ship was registered. That's weird. I didn't think I changed any of this. I haven't touched this script in a while, other than I think I set it up to not send the command to self-destruct so that I could see the ship actually come to a stop. Why? All right. It could be a problem with my ship script actually. The ship may not be sending the acknowledgement. Okay. Recompile. Let's check that one. Delete that. So this is a whole extra stage of debugging that I can't do entirely within Visual Studio, but it is nice to be able to do what I can there. Alright. Wish I could just wait for you to see. Alright. So we'll watch what the ship says it does. Ship is not doing anything. Alright, the ship should be logging out that it has received instructions from... Ooh. Oh, I did move this around, didn't I? Ah, damn. Okay. So this is something I shifted where this IGC stuff was registered when I... Oh, yeah, that's fine. When I was setting up the test framework. because initializing it in the constructor caused problems with the way my mocks worked. But it looks like maybe not doing it in the constructor is going to cause problems with the way. Ooh, what if? That'll work? That should work. Hold on, I'm going to try something. So I'm calling this, so yeah, sorry. To explain what I think is happening is normally these get registered right away. As soon as the programmable block is built, this constructor is run. And so the listeners get registered, and the listeners are what are waiting for that registration call from the brain block. But the way I switched this, I call, yeah, there it is. I call init IGC in the main method, which only gets called if the script executes. Okay. And so what I need to do, because at this point, when the ship first comes in, the constructor's called, but the script never executes unless it's told to. But what I can do is tell it to. Wait, is it? Okay, now I don't remember which where the update frequency is stored. Runtime.update frequency. There we go. That's what I want. Wait, hold on. Is that going to screw me up? So what I want to do is say runtime.update frequency equals update frequency dot once, which will tell the script to execute once and not again automatically. It can still get called by like the IGC stuff, but if the IGC stuff isn't listening, it won't find it. So I need to force it to run once first, so that it will listen for calls from the brain. But I do use this elsewhere, so I want to make sure this isn't gonna totally screw me up. Oh, I just set it. I don't check it. Okay. Yep. No, we should be good. That should work. I think. All right. Deploy. Go through this whole thing again. Edit, browse, refresh that. Okay. Copy. Replace blueprint. Projector, blueprint, place. Recompile the brain script for good measure because I don't remember if I did, and hit go. And fingers crossed. Poop. Alright, I guess I should have been watching the logs. Recompile you because you don't know that. Yeah, you're still waiting on a ship to register. And it's got nothing. does seem to have the right code. Oh, that's embarrassing. So I'm calling this init IGC method. The idea was to, to make sure this is called before I do anything else. Oh, I wonder if this works. What I didn't realize is this is only called if the source of the call to this script was the IGC, which of course it isn't when I call it this way. Yeah, this needs to be moved outside of that if block. All right. You know what? I can just I can change it here, but then I need to restart the whole flow. Yeah, I gotta do it all again. Okay, that's fine. So this is the kind of constant churn that I was looking to eliminate with those mock classes. Now, this particular case isn't something I can test with the mock classes, at least not yet. It'd be cool to set them up so that I could actually test with the, brain calls the ship and the welder and all that, and simulate that too. Like, that'd be very cool. But that's a lot more work that I don't want to do. Oh wait, yeah, this is fine. Place, it's good. I hope I did all the right steps there while I was talking and not necessarily paying attention. But I think I did. Alright, I am gonna go ahead and look. I think it's gonna work correctly this time. It'd be nice to see if an error gets thrown or something. Come on. Yeah! Okay, so the self-destruct is still in there, but you may have seen it, well, yeah, now you're gonna get to watch it explode. Ooh. Oh, just run it again, and I can stand back this time. So the self-destruct command is in there, so it's once it reaches its goal, it's going to be instructed to fly off into the sunset and disappear forever. But before it does that, you can see it execute the instructions where it comes out, comes to a stop, right on that 8-meter mark, and yeah, then rides off into the sunset. Cool. So yeah, so that was the whole thing. That's what it was supposed to do. And it's a lot easier to test the inner workings of all that using these mock classes rather than going through that whole process every time. So I think this is going to be a great boon, and I think I've got it set up. I think I have it set up in a way that will be easy to expand upon and make work across, whatever scripts I want to test. So, looking forward to making use of that. Yeah, so that's the recap of what I did offline. And I swear it took me longer to describe what I did than it took to actually do it. That's not true, because it didn't take that much time to do the actual code writing. It took a long time to do the debugging of the little bitty errors after the fact. And I kind of wish I had you guys for some of those, because it might have helped me get there faster. But that's all right. That's all right. I'll have you for any that come up today, right? You're my rubber duckies. Which might sound really weird to you if you've never heard of that thing before. But if you are a programmer, you may have heard of rubber duck programming or something like that. Which the idea is basically that, well, so start with this. If you are a programmer, have you ever been struggling with a problem and gone to talk to a coworker or a friend or whoever so that you can explain to them what your problem is so that they can help you solve it. And you go over and start talking to them, and you're maybe halfway through explaining what the context of what's wrong. You might not even have gotten to what's wrong. You're just explaining to them the context, and it's like, oh, I just figured out what happened. Thanks for your help. Bye. So the idea is that people will do that. I think people will literally do that with a rubber duck, an inanimate object. It does not have to be an actual person, because that actual person doesn't usually end up involved. Usually just the process of explaining it out loud is very frequently enough to allow you yourself to find the solution. And I've actually really found that to be true doing some of this programming through Twitch. The fact that I am keeping my stream of consciousness vocal is kind of keeps it focused, and yeah, it definitely helps you find stuff. So hey, maybe that would be I mean, I know I don't, it's not like I have any kind of consistent chat or anything, but you know, that's what I can call you guys. That's what I can call every streamer's got a nickname for their chat, right? You guys are my rubber duckies. Any objections? No? No? You guys like that? I'll take your silence as confirmation. I don't know if there's anybody watching. But yeah, that's what I've done, and it's pretty sweet. I'm gonna do some other work, but actually I kind of want to show off. Hold on, I'm gonna switch back. I did. You can see Visual Studio on the big screen. So yeah, one thing I did do too, that I noticed made a difference in the number of these tests that succeeded, was I tweaked the time step ticks from 10 down to 1. So the time step ticks, what that variable is supposed to represent is whenever I'm evaluating a new state, right? So we have our start state where the ship starts, it's not moving, it's in some position. And like I described, the way the algorithm works is it says, all right, I'm going to pick a combination of thrusters, and if I turn them all on, what state am I in next? And part of that depends on how long you're doing that for. And my kind of default to work with has been 10 ticks, and there are 60 game ticks per second. So operating at 10 ticks is every sixth of a second, basically, we're reevaluating the state, which is a nice balance, I think. The idea was that it would be a nice balance between granularity, you know, having fairly precise control over where we end up, but also not having way too many steps, because if you have to go through thousands of steps to get where you're going during a debugging process, that's really tedious to try and look at manually. Also, it can create a much larger search space for the algorithm, so that can come with its own problems. But yeah, basically 10 ticks was supposed to be kind of that balance, and I think it worked well for a lot of cases. But there are still those cases where we're only, I know, only every sixth of a second, but when we're only going 8 meters, it takes less than 2 seconds for the ship to get there. So I think it was less than 2 seconds. I don't know. Well, you can see here, the solution was found in 1, 2, 3, 4, 5, 6, 7. I believe this is an 8th instruction of nothing happening. 9, 10, 11, 12. So that's 12 sets of instructions. Each one went for a sixth of a second. So I guess this is 2 seconds. So I guess it technically takes a little more than 2 seconds to go those 8 meters. But still, that's not very much time. Like I said, I'm talking 12 steps here. And that's only to get within 3 meters of the goal. So I guess that was only going 5 meters. So, but it's possible also because I'm only ever firing the thrusters at maximum or zero. Right now, I'm not accounting for any kind of, half power or whatever fractional power. Uh, there are actually some positions in space you just can't reach, um, because I've limited my ship's capabilities by only allowing anything to change every sixth of a second. If I take this back and only run it and check it every 60th of a second, 10 times as frequently, you can get much more precise results. It probably takes longer. I don't know why I said probably. It's going to take longer. It might not take a lot longer, but it's definitely not going to take less time. So it'll take longer. Probably not enough to matter on short distances. As I was testing, it definitely is enough to matter on long distances. But I think that was the big difference maker, though, is I had a lot more success running my tests when I used a time step tick of 1 tick, a time step of 1 tick. So here I can actually probably try running like 8 to 16. Let's see. I don't know. I'm just gonna run it and see what happens. And I'll let that go, and I'll talk about what I want to do next, and hopefully it'll resolve. I still haven't found I want to mess around with my tests here a little bit. Oh, something just died. That was quick. Oh, fuck. Right. Right. All right, this will take a little more experimenting. So yeah, the whole reason I moved these out of the constructor was because my mock, it's not up there. I apparently closed it. My mock program is creating the mock runtime in its constructor. But because it inherits from program's constructor has to run first before mock program's constructor. But yeah, I moved them because IGC hadn't been initialized yet, and it's calling IGC stuff. And I moved them out, and my solution was, oh, hey, here, I'll put runtime in there. But runtime hasn't been initialized either because I had to mock that. Okay. So I'm going to have to find a different solution for that. And it might be that when I'm testing, my program has to inherit from the mock program. That might just be what it is. Yeah, I might just have to make small changes when I do that. Anyway, my simple solution for right now is just going to be to comment this out, and that'll allow me to run my tests. Oh yeah, don't need the brain open. I can close that. I can close that. Yeah, I'll close it. All right. So yeah, so we'll let that run for a bit. See if anything comes of it. Oh, there it goes. Hey, it did. There we go. So that says to me that at 8 meters ahead, 9, 10, 11, 12, 13, 14, and 15 meters ahead, it successfully found a goal. It found a path to the goal. And of course, all of these instructions are just going to be thrust front a bunch and then thrust back a bunch to slow down. Oh yeah, I guess it even cuts it off to open a separate file to view the complete output. But yeah, the whole thing. It ran 7 tests in 1.6 seconds. That's not bad. Not bad at all. So yeah, that's the power of having this. Well, that's one of the powers of having this in here. You want to see the other power is breakpoints. debug a test. And then it'll stop at these breakpoints. And Visual Studio will chug a little bit as it loads everything in. Yeah. All right, I got to remind myself real quick of the step controls because they're different than in IntelliJ. Which is what I'm used to. Okay, F11 is in, F10 is over. It's good enough for most. I'm just gonna use F10. So as this, I can say I can stop. So stop before executing this, and I tap F10 and it says, all right, I'm gonna execute this line and just that line, and I'm gonna wait here. And so now I can see this open set is actually shown down here to be initialized. It's got some of the information like being size 0. Here we can see our start node. Well, actually, the start node doesn't even. Oh, I guess it does show up here, but it's null because again has not been initialized. We step over. Now start node has its information. It's got no command. That's going to stay. Most of this is just the defaults, but it already calculated the heuristic of the start state at 2.4 seconds. There we go, 2.4 seconds. That's how long it takes to get there. And 144 thruster fires. And then we can see, yeah, our open set is currently size 0, but here we're about to add it. Now it's size 1. And I can even look in here at the set of elements and it'll show up there. Oh, I tried to expand the set of elements and Visual Studio did not like that. There we go. Oh, because this is so big. Well, yeah, because it's like 100 million. I probably didn't need to make it initialize it that large. But, oh well. I did that because when the min heap has to expand, it takes a lot of execution. It was causing issues in the script. Okay, well now Visual Studio is just gonna chill. So while we're waiting on that, if you don't try to do anything too crazy, like open up a 100 million size list, it does better. Oh, good, it just straight up crashed. Here we go. I promise the stream is not offline. Here, let's let's switch you back to this. It's coming back. Here we go. All right. We got it back. We got it back. Anyway, that is the real power of being able to run it in here. I mean, it's a lot faster, but also the fact that I can step through everything and view the variables, that is the most powerful thing that I'll be able to do by being able to run these tests that way. Yeah, that's what I'm really looking forward to and what I really missed running it the old way. So anyway, that was cool, and that was fun to be able to talk through, and now I want to talk about making more updates. So there are a couple things that I was thinking about doing. Well, I guess one of the things I had on my list was to tweak the rounding limit, and I suppose I already did that, because I definitely wrote that down before I actually made that change. So bringing that back to 4 was definitely part of that. But honestly, one of the things that I thought about doing instead of doing this awkward rounding, because here I'll show you where this is used. I'll use it in my. This is mostly in the cost comparison. This isn't the only place I use it, but it's definitely part of it. Oh yeah, I do it in the state too. Actually, yeah, here's where it's really like atrocious looking. So when I'm looking at a state of the ship, or really a state of the, well, the state of the world, but right now all we care about is the state of the ship. That includes the ship's position, its linear velocity, and its angular velocity. So in order to compare two states and determine if they're equal, I need to see if the positions are equal and the linear velocities are equal and the angular velocities are equal. But I talked about rounding error earlier. Rounding error means they're not equal. They're almost guaranteed to be slightly different. And so to account for that, often what you'll do, I'm sure there's something built into C#, but usually there's some kind of function that's like a floating point compare that will, instead of checking if they're equal, they'll check if they're within epsilon of each other. Epsilon's the commonly used Greek letter for this difference. I don't know exactly why it's math. It was probably determined during, the Greek Empire. But at any rate, wow, lost that train of thought fast. Yeah, so you'll compare two doubles or floats and see if they're within a certain distance of each other. And if they are, they're considered equal. It's like, all right, it's merely off by rounding error. So normally I would just do that. But because I'm using the state in maps as a map key, I also have to make sure the hash codes are equal. The hash code is a way to pseudo-uniquely identify well, not quite uniquely. What's a better way to? I should probably Google it and get a more precise definition. That's better than what I can just come up with off the top of my head. But essentially, a hash code turns an object that in this case includes a position, a linear velocity, and an angular velocity, three-part vectors into an integer. And the idea is that this integer is, well, hopefully it's largely unique compared to other objects' hash codes. It doesn't actually have to be unique, because what it does is objects with the same hash code just get bucketed together. But essentially, yeah, when you look at a map and you say, okay, I want to get the map with the key of this state, rather than checking all of the points of the map to say, okay, is this state the matching state? Is this state the matching state? Is this state the matching state? You calculate a hash code. The hash code says, okay, it's this integer, and I already know that any states I have with this integer are stored here. So it looks at the states with that hash code and then checks if those are equal, using the equals method. I hope that made some sense. That was a very ham-handed and probably not perfectly accurate explanation, but I think it's I think it's accurate, just maybe a little awkward. But yeah, so the thing is that if two objects are considered equal, their hash codes also have to be equal. Like I said, if two objects' hash codes are equal, does not necessarily mean the objects themselves are equal. But so their hash codes group them as rectangles. Groups say a rectangle and a square, both in the rectangle bucket. And then when you're actually looking for equality, you say, okay, is this rectangle my square? No, it's not, but this square is my square. So, rectangles would have a different hash code, and triangles would have a different hash code, and pentagons would have a different hash code. But the rectangle and square would have different equals values. The right triangle, isosceles triangle, and scalene triangles would have different equals values. Man, this metaphor is getting out of hand. But yeah, so because if two objects are equal, they have to always have the same hash code. it's not sufficient to define equals, since I do need hash code. If you don't need hash code, you could define equals basically however you want. But since I need hash code, equals has to be defined consistently. And if I just define it as, hey, are the position of the one and the position of the other really close, that might not be good enough, because even if they're really close, they could generate different hash codes. In fact, they probably will. And that's bad. So instead what I did was I first round the values to some number of decimal places. In this case, like I've shown, I cut it back to 4 and say, hey, are these equal? Out to 4 decimal places, are these two values equal? And then to make that consistent with the hash code, we round the value to that same number of decimal places, so that when one has its value rounded to decimal places and then multiplied by this big old prime number, and the other has its different position rounded to the same number of decimal places, if that's the same, then it will be the same here, multiplied by that same weird prime number, and do the same thing for all three, and it comes together. Prime numbers are used because they help, and I think they're specifically supposed to be very large prime numbers. They help make the distributions nice, so that they're mostly unique. But yeah, that's the nonsense that goes on over here. And in the cost, it's similar. It's a lot less complicated because I literally just use it in the compare to. And technically these time comparisons aren't necessarily equivalent to like the positions and velocities here, so they don't even necessarily need the same types of rounding, but I kind of did it to be consistent, and maybe that's bad, but actually I guess that's kind of what this rolls into, is this doesn't have to be the same. But the time cost is still susceptible to rounding error. It's just not necessarily going to be the same kind of rounding error, or have the same differences as the positions have. So I was thinking about what I wanted to do here, because when I wrote the very first iteration of this algorithm, I was actually calculating time using whole seconds, integer seconds, because I'm like, oh yeah, I want to use an integer because then I don't have to worry about rounding error, because I already know that's a thing. So I used integer seconds to set up my time costs, and that was shown to be a very big mistake very early. So I didn't waste too much time on that, because as we saw, the distances I was testing, it takes 2.4 seconds to go that distance, and that's 2.4 seconds to go that distance when you speed up and slow down. When I was first writing the algorithm, I wasn't even slowing down, I was speeding up the whole time, so it was less than 2 seconds. Which means, and I'm evaluating a new state every 1/6 of a second. So let's see. If you take your initial state, you say, hey, I think it's going to take me 1.8 seconds to get there. Cool. Call that 2. Round it up, or maybe we round it down because we're supposed to round down most of the time. Either way, so let's say it's 2. Let's say it's 2. It's going to take me 1.8 seconds to get there. All right. Let's look at the next state. The thruster fires forward, moves me towards the goal. How long do I think it's going to take me to get there from there? Well, I've only been moving for 1/6 of a second, so I'm betting it's about 1/6 is 0.16666, right? So I'm betting it's about 1.63333 seconds. Guess what? That also rounds to 2 seconds. Those get evaluated exactly the same, and the algorithm is terrible. Whole seconds don't work. Not even a little bit. So I switched to turning it into a double and using decimal seconds, which is much better, but still has the weird rounding errors. So I spent a little time thinking about this, and it occurred to me I have the perfect integer time measurement sitting right in front of me. And it's game ticks. I can calculate things in game ticks because my script can literally not run more often than once per game tick. That is the most frequent it's even allowed to run. And most likely, that's the most frequent the game engine even reevaluates its own states. I don't know exactly how the game engine works. I'm not a game developer. I just like coding AI. But yeah, like that is literally the most granular it will ever make sense to be, is one game tick. And 1/60th of a second is a really awkward amount of time to work with when so many of my, not the tests, when so many of my calculations are in real life physics terms that rely on time in seconds relative to the acceleration in meters per second squared and velocity in meters per second, so on and so forth, because that's how the physics works. So I do have to use seconds in those calculations. But at the end of the day, when I'm looking at time cost of how long it took me to get somewhere and how long it's going to take me to get the rest of the way, there's no value to be gained in having a value that's in a fraction of a game tick. So I think what I want to do is change at least my cost times and as many other instances of time that make sense to be in terms of ticks, because then they can be integers. Like there's still going to be there's still going to be floating point calculations in the kinematics equations, like I pointed out, but they get rounded at the end. You know, multiplied by 60 and multiplied by multiplied by 60 and rounded to the nearest integer, or maybe always to the floor. I might have to think about that too. I think nearest integer is fine though, since everything's always being rounded to the nearest. I think nearest integer is fine. Yeah, and that's I think that will I think that will at least eliminate a source of future headaches. That's really what it comes down to. It's like, yeah, rounding this to 4 decimal places is fine, but it's kind of a pain to deal with, and it doesn't have to be the same kind of rounding as these, which don't even necessarily have to be the same rounding as each other either, but it's fine. Yeah, it can just be its own thing, and it can be in terms of ticks, and that'll be great. So that's the first thing I want to do. You know, the first thing after all this other shit I just did, but all I did was talk. So there's that. Uh, that's the next thing I wanted to do, was convert these time costs to an integer value, and that integer value is going to represent game ticks. So let's do that. Let's do that. Good chance I'm not going to spend a lot more time in Space Engineers itself today, for better or for worse. But yeah, let's. I guess I could. I don't know. I don't know if the. I don't mind the the background noise of the thrusters humming. I could probably turn it down a little bit though. Turning this down a little shouldn't affect my mic. They're separate. Yeah, that looks right. Just in case that's a little annoying. I don't know what other people think of it. So, okay. So yeah, this is going to be, finding all these usages is going to be interesting, and finding the line on where we switch things. But yeah, this is what I want to try next, because I think it'll eliminate some headaches. So, first things first, this becomes an integer. And I think, so even though using the name time is fine, I think I want to change this name to be ticks, largely so that it's very clear, it can be very clear in the code when a time value is representing time in seconds, in which case I'll name it time, or time in ticks, in which case I'll name it ticks. So that's what I want to do. You know what? I should just copy the word ticks so that I can just paste it a whole bunch. All right, so don't need that. Ticks equals other dot ticks. Ticks other dot ticks. So yeah, so this is all still the same. So our comparison is if the time cost in ticks is equal between two states, well, two costs, then we compare the the thruster counts. If the tick time is different, we always do the comparison based on the number of ticks, because that's our primary differentiator. I'm optimizing the algorithm entirely for fastest time right now, but when two things have the same amount of time, I'd rather we just fire the single thruster. That ticks. That'll be the same. Plus compares. Cool. Those look great. The other advantage of changing this name from time to ticks is that it'll obviously show up in the code. Okay, the state doesn't directly have a cost, so I'll get rid of that. Yeah, it'll show up in the code very clearly when I was using cost.time, and that I'm going to need to adjust something there. So let's start with those locations. Time step, tick time. Oh, yeah. That's, wait. Oh, because this is a cost. Okay, so this is where I'm trying to create a new cost. And so used to be that I calculated our time step is in seconds. And so that was the number of ticks, or I guess the number of seconds per tick times the number of ticks in a time step, which is defined in here. And so now the number of ticks in a the time step ticks is just, that's all we care about. So we're just going to eliminate the time step variable. I think that's right. I think that's right. All right, so we'll see what shows up here. All right, so this is in our generate neighbors. So this is when we're looking at a parent node, which primarily the parent state, and determining based on a command or a list of thrusters we want to fire what the new neighbor state is. So here's this. So we're calculating a new linear velocity by getting the velocity based on the original linear velocity, the acceleration based on the thrusters we're firing, and the amount of time that's passing. And the amount of time that passes is going to be, so yeah, so this is fine. All right, I changed my mind a little bit. I do want to use this variable because this is still going to be a common calculation, because we are going to have to convert back and forth between our time step in ticks and the amount of time in that time step. So, but I am going to rename this. So I'm going to rename this to time in step. So a step is now calculated in ticks, but this is the amount of time in seconds. Oh, here, maybe we'll do this. Seconds in step. I like that. I like that. This is the number of seconds in one step. So like right now I've got time step tick set to 1, so it's 1 times 1/60th. Yeah, that's fine. All right, so seconds in step is our new thing. So, and that is what we want this to be. It's, we're getting the velocity, say if we start at this velocity and are accelerating at this acceleration vector over some amount of time, and that amount of time is seconds in step, that is our final velocity. Perfect. All right. Huh. Definitely missed something here. This section of the code has never been executed. So this is a section of the code where, oh, I wonder if this is actually why my long distances failed. Oh, that's actually interesting. Sorry. So this is the section of the code that says the ship is going to accelerate to its max speed and it needs to coast for a while before braking again. But in the short distances that I've mostly been evaluating, that never happens. We never actually end up needing to accelerate all the way up to the 100 meters per second max ship speed allowed in game. So this code never gets executed, which is good because this is a nice little infinite loop. So what we did here was we calculated the amount of time it will take to reach maximum ship speed, and then the amount of time left on the so the time remaining is the amount of time left in this time step, the amount of seconds left. So actually, yeah, let's rename this to seconds remaining, to be clear. And I'll go ahead and rename this seconds in step. So seconds remaining is seconds in step minus time to max, which I suppose maybe is also worth renaming to seconds to max. I know that I said I was going to use time as seconds and ticks as tick time, but this is feeling even more clear, so why not? Where I notice it, I won't search for every instance of time in the code and replace them all necessarily. Not right now anyway, but I think this will be more clear. So yeah, so this calculates the amount of seconds remaining after we've accelerated to max velocity. And we're looping for as long as there are still seconds remaining, but I'm never reducing the value of seconds remaining, which means this is never going to change. So remind myself, what am I doing here? So we calculate a new velocity. Right. Tick time. Oh yeah. We're going tick by tick. That's exactly what I said. Approximation of movement by value new velocities tick by tick. So yeah, so at the end of this, what I should be doing is seconds remaining minus equals tick time. There we go. So I noticed I successfully calculated routes up to like somewhere around 100 meters out. Again, only in a straight line in one axis. I was having some problems still routing along multiple axes, which is annoying, and a different problem I need to solve. But I was going out to about I got a little over 100 meters, and it was still fine. But when I started getting closer to 200 meters, um, it it started crashing on me, and it would just run and run and run until eventually I ran out of memory, and it threw an out of memory error. And I wonder if I actually hit that threshold somewhere in between 100 and 200 meters where the ship does accelerate up to max speed before slowing back down, and we hit this stupid loop, and I got stuck and basically memory leaked. It doesn't seem like this should technically cause a memory leak, but yeah, it's possible that's what happened. Anyway, that should help, because yeah, now seconds remaining actually gets reduced, so it's not always greater than 0. Cool. Cool. Yeah, that could have happened. All right, anyway, that resolves all of our math bits in here. Oh, I just realized there are some commented out things that I need to get rid of. So here I was doing some additional rounding that just got kind of excessive, and I ultimately figured out I didn't need that. The rounding in the state class was sufficient. So this was me setting the angular linear velocities via rounding, but here I'm just doing it without. I don't need that anymore, and I did the same thing right here. So it'll just clean up the code a little bit. And this looks like the same thing for position. So this is the state where, oh yeah, this is just going to be setting this to seconds a step, right? So we're getting the position based on our starting position, starting velocity, acceleration over some amount of time. That amount of time is seconds a step. So that's fine. This one is different though, because this is creating a new command, and the cost of a new state is always going to be exactly one step more than the previous one. So we had our previous cost, we're adding our new cost in time and in thruster count, and the time is now not time step, but it's in ticks. So it's the program dot time step ticks. That's the integer we're looking for. All right. I guess this stuff is all fine. All right, more math. So again, if we're going to reach maximum speed, this is in our heuristic function, right? Yeah. So if we think we're going to reach maximum speed before we have to start braking again, steps accelerating are math floor of the time it takes to reach max speed divided by seconds in a step. Same thing for this, seconds a step. All right, that's an easy replace. And this is the same thing. Seconds in step. Seconds in step. All right. And here's our cost again. So this was, we calculated a time in seconds. And we want this to be a time in ticks instead. And since these times are entirely based on the kinematics calculations, I think it's totally fine to leave these as time in seconds. And we'll just make this, our time in ticks is max time times something about, oh, I don't remember what the actual, I think it was tick time. Tick time. So this is the time in seconds times the number of ticks per second, which results in a number of ticks. And then we'll just cast to an integer, which I guess I want to know. Let's see. C# cast to int rounding. Is it a truncate or is it a round? Casting double as int is just a truncate. Okay, that's what I thought. That's what I thought C++ had been anyway. Okay, so this is effectively going to be a floor, which I think is fine anyway. I think that's what I'd prefer. Yeah, I don't know. It's possible that a straight rounding is still fine. I definitely don't think a floor is going to break the algorithm. I think there's a chance that a round actually technically breaks the algorithm. Probably not in a way that would really be significant, but if I did a round, it's possible the algorithm would find a not quite perfect solution a little bit before. If we do a floor like this, it should find the perfect solution. It might take a little bit longer than it would have otherwise, but should be all right. Okay. Is that really the only place I use cost? I wonder if, I don't know that, yeah, I mean, there's no red showing up on my bar. I mean, I could do a quick build and it should tell me if there are any build errors. Because there could be something in one of the files I haven't opened, but I guess Node might. Because Node has costs, but it's just storing them. Oh, here we go. Oh, and my tests. Well, that makes sense. Okay. Oh, all right. So I'm gonna, yeah. Okay, that's fine. So I basically just need to multiply each of these by 60. And that should be right. And I'll run the test again to make sure that matches, but 2052 times 60 is 123.12. 1870 times 60 is 112.2. 1.965 times 60 is 117.9. And 1.703 times 60 is 102.18. Hold up. Oh no, that is right. Oh, I just didn't put them in order. Right, I did that intentionally, I guess. I thought it was odd that I had the largest one, then the next largest and the third largest were swapped, and then the smallest one. But I actually did do that on purpose to make sure they would get reordered. Okay. What other nice little warnings do I have? I guess I should check these. These shouldn't be an issue, but oh, yeah. I think I had that as like an emergency stop for the. Wait, is this the? Oh yeah, this is the brain. Sorry, I looked up here. I thought that was the welder. This is the brain script. Yeah, because this got copied over from an earlier build using a different algorithm. I had like an emergency stop button that's really just not needed for this one. So actually, yeah, let's just take it out. It's fine. I don't really need to clean up the warnings necessarily, but I can. So okay, that just says updated. Unreachable code. Oh, I know that. Yeah, I just put a return statement in my print node data so that it wasn't printing everything all the time. Processor architecture. That seems fine. That's just, yeah, that's fine. That's not really anything I have to worry about. Cool. Okay, that should work. So the test I changed. Let's make sure this still runs successfully. I should probably run all my tests and make sure they still run successfully. But cool, that one was good. Oh yeah, I guess the literal values didn't matter at all, did they? I was just reordering them. All right, I spent more time on that than I needed to, but it's okay. Multiplying 4 numbers by 60 wasn't that much time. Yeah. Here, let's run. Oh, I guess I did do a basic test. Oh yeah, this doesn't have anything to do with the actual. They're just example costs. I don't think I've changed anything in kinematics for a while, so those should run just fine. And I don't think I can even run this since it has parameters now. Yeah, I'm probably supposed to change that. Originally, originally I was running this so that I could run it, on its own. I could just, this is a test method, it's fine. Make it private. Hell, I think it could even be static. There. Run all tests. It'll take a second to run this one, but it passed last time. Should pass this time. Probably good to make sure it actually does. Actually, very good to make sure it actually does. Since I did change something kind of fundamental about the code. I really wish I'd run this on a smaller sample. I mean, I could just kill it and run it on a smaller sample size. I don't know why I'm saying I wish I had done something when I can just do that thing. Is it just me, or is this taking longer than it took the last time I ran it? That's not terribly encouraging. All right, I want to do some searching. Okay, no, I don't care about those. No. Why? No, don't search this. Oh, it's because, oh yeah, no, search this. Okay, cost 0, 0, that's still right. Yeah. Yep. That looks right. Oh, no, that's very wrong. That's very wrong. Divided by. I want it to be the time times 60, which would be the time divided by 1/60th. There we go. Okay, that's better. Oh, we already saw these. Does that mean we're done? Okay, these are nothing. Okay. All right, that's better. Try this again. Please. Maybe. You know you want to. You know you want to. Not going to. Well, we could run it in the game and see what happens. All right. Oh, I mean, I can let it keep running, I guess. Although if I change some of this, it might freak out on me. I don't know. I mean, I guess it's already past this point anyway. Okay. So yeah, I want to bring that back in. I'm going to deploy this. Is that all I need? I think so. All right. Deploy script. I assume you'll deploy while that test is running. Looks like it. Okay. Here. I'm gonna flip it back. Wait. Oh, that's not. Hold up. Sorry. I had a different page set up than I thought. There we go. Oh man, I wonder if I messed that up earlier. Didn't have Visual Studio visible the whole time. Probably wasn't too bad. Boom. All right. Ooh, I should turn the volume back up probably. Okay. Yeah, we are deployed, so come in here. Edit, browse scripts, refresh. Grab you. Okay. Copy. Place blueprint. Right here. Place blueprint. I don't think you actually need to be recompiled, so fine. And go. Alright, building. I'm gonna go. Oh, there was one other thing I meant to do. Let's see what it does. Because I turned off most of the logging. Forgot about that. I meant to turn that back on. But we'll see if anything shows up here. In the meantime, I'll pop back in here. Oh, it is still just displaying the frontier at least. Okay, so I can see that it's trying, and just not succeeding. Damn. Okay. That is kind of nice to see that go by, though. So yeah, you can see the. So it's processing, I guess. I don't know if that's 6 or 7 or 7 or 8, but I'm gonna say roughly 7 nodes every game tick. Man, that's not a lot. I expected it to get more than that, but I guess my heuristic function's gotten pretty big. But yeah, I'm already up to a frontier size over 200,000. The frontier size is the number of neighboring nodes that I've identified that I haven't explored yet. So yeah, that's just gonna grow and grow and grow until game crashes. So that's fine. Just kill that. Actually, I won't delete this ship right away because I might just reuse it. Let's flip back here. I might not now that I have. Yeah, this is the perfect opportunity to see my new debugging in action, right? All right. So let's comment this back out so that my test will run correctly. I'll figure out how to fix that somewhere down the line. Ooh, actually, I have a thought. Wait. Did that work? Yeah, that should work. Oh, except does this have to use a default constructor? Can I? Oh wait, I can just make 2 constructors. Oh, there we go. That's actually kind of funny. Yeah. I think this will work. Okay. Oops. Cut. Paste. This is terrible. There's got to be a better way to do this. But, hint. Oh, this could be a. All right. So my idea here is that my mock program will call. So in game, it will call. I switched back to this, didn't I? Yeah. In game, it will call the default constructor. But I'll specifically have my mock program call this dummy constructor that has a parameter, so that way it'll get built with this and it won't call any of those, since I don't care about any of those. Oh, and I guess I need to move this if I'm going to do that. Cool. Yeah, then I don't have to change anything. So I have to have this weird little stub in there, but I don't have to change anything. Every time I want to switch between running a test and running it in game. There's got to be a better way than that, but hey, I think that was fairly creative. Okay. So here we go. So we want to call this. We want to, do the single run, 8, 9. Yeah, that's fine. I want to some steps. Where do I want to start evaluating? I want to see what happens, mainly with the neighbors. So I'm going to start out putting a breakpoint here, and we will debug. time to see the power of the debugger in action. Okay. So I'm not going to open up the open set because I already know that's a recipe for the for Visual Studio to crash. But yeah. See, I can see my current state is, or my current node, I guess, has the 0, cost, estimated that, oh yeah, no, that actually makes sense. So it's estimated that it's going to take 144 ticks to get there, and we're estimating that it's going to take 144 thruster activations to get there as well, which is exactly right because I'm planning on activating one thruster on every tick. The forward thruster on the first, or I guess it's the rear thruster, the thruster that moves the ship forward on the first half of them, and the thruster that moves the ship backwards or slows it down when it's moving forwards on the second half of them, so that it comes to a stop, moving at 0 at the very end. So that actually, that is exactly right. It should, the thruster count and ticks should be the same for this when you're expecting to go along one axis. Has no parent, state, no velocities. That's our sample position. Cool. Great. F10 is my steps, right? All right. So, oh, I generated neighbors. That's fine. So thrust back. So how did I name these? We were looking at 144, so 145. Okay, yeah. So this actually moves me. This is the thruster that moves me backwards, so that's fine. Or that's what I'm assuming from the H-score calculation. H-score 1-1. Yeah, parents. Yeah, 144. State is moving. Sure, whatever. Oh, there we go. Pin that. Maybe move this around while it's pinned. Now it's gone. Oh. Here we go. Here we go. Awesome. Okay. This one that moves us down. Oops. Moving down, we still expect it to take 144 ticks to get where we're going, but it's going to require 3 extra thruster activations. Yeah, that actually sounds right, because it H-score. Yeah. Okay. Yeah. So because we activated the thruster that moved us down, we're also going to have to activate the up thruster to slow us to a stop, the up thruster to get us back to the original axis, and the down thruster once more to slow us to a stop on that original axis. So that makes exact sense that added 3 thrusters to the count. And a lot of the others should be essentially the same. Yeah, same idea here. I get to the ones that move us forward. There you go. Thrust front. 143, 143. Yeah, should take 1 less than before. Yeah, front and back gets us nowhere, so it's still 144, 144. Oh man, yeah, there's so many. And then at the very end is the last one. That was our fire no thrusters. Yep. Same as before. Cool. That all adds up. That all adds up. So let's see. We can iterate through each one. It should add them. That should be fine. Best G-score is group of costs. Should all work fine. All right, I'm going to assume all these are working fine, and I'm gonna allow those to add and loop back around and let it pause at my breakpoint again. Oh, what's the hotkey for that? Oh, continue. There we go. I don't know. Is there a hotkey for continue? I'll just press it. All right, so now current should be the best neighbor from before, which should be the one that fired thrust front and should have a thrust front 1-1 143. Oh, you know what? We should pin this too. Perfect. Yeah, 143 143. Cost 1-1 to get there. Yada yada yada. That's great. Step over. The neighbors should be much like what we saw in our other one. Just back. 2-2. 44 144. 44 doesn't seem right. Oh, wait. No. Yeah, it does. Yeah, it does. Where is it that we get? Front? Yeah. Alright, I mean, yeah, right now it seems to be doing what it's supposed to. 2-2, 142, 142. Yeah. Actually, I don't need to get that there. I can just leave this open down here. Maybe. Does it collapse every time? Nope. It stays up. Okay. Unpin. Or wait. That's fine. Unpin. So okay, yeah, so I'm gonna watch these. And they should just be ticking up little by little. Looks pretty good. So I'm guessing something happens at the end that causes it to, because this is exactly how the algorithm should be working. And now we're reversing. Wait, we're reversing. Oh. Oh. We shouldn't be reversing yet. Okay. Something screwed up. And it was somewhere before 37. Alright. No, that's informative. Alright. Kill this. And debug again. I can also set this. I should be able to set the condition. So it'll only break here if, we'll say, tick nodes processed is greater than 30. Because, alright, so now it should run, break. Alright, we're on on 31. Still looking good. 30 is fine. 31's fine. 32's fine. 33's fine. 34's fine. 35 it screws up. All right. Let's find out why. All right, we'll reset this to greater than 33. 34 was fine, but somewhere in its neighbors messed up. So kill this, try again. This is so much easier than looking at the log output in Space Engineers script. So very much easier. All right. So our current node is 30. Oh, because the tick nodes processes up by 1. Yeah. That's fine. Okay, so the next one. There we go. That's what we wanted. This one's good. This is the one we wanted to be evaluating. But what I want to know is why we didn't evaluate the next thrust front next. So G-score is 34, heuristics 110. Let's generate neighbors. Let's meet our neighbors. Actually, yeah, I'm gonna pop that out over here so that I can get a nice look at them. Okay. Thrust back. So our current, yeah, there it is. Current's 34. Estimate that it's going to take 110 ticks. Thrust back. Then we're saying we're estimating that it's still only going to take 110 ticks, but it's also only going to take 109 thruster activations? That just seems straight up wrong. That's cuckoo pants. Alright, let's see what the rest of them look like. 109, 109. That's also, yeah, seems wrong. 110, 110. 109, 111. Yeah, see, why is thrust down 109, 109? And thrust up is 109, 111. This one seems more likely to be accurate. 110. Yeah. 109, 108. Thrust front 109, 109. That actually that is what I would expect. Continuing to move forward. Heuristic goes down by 1. That's exactly what we expect to see. Why so many other things? Well, okay, that one makes sense too. Or except the, oh yeah, no, that one's right. It's just that the G-score is 37, so yeah, that's right. Yeah, those all seem right. Just the ones that involve the backwards thrust seem wrong, or some of them do. And then the one that actually ends up getting used is the 0 command. I remember that's the one that gets evaluated next. And why would its heuristic be 108? All right. Well. Yeah, these are definitely goofy. I wonder if... Huh. So nothing, I will say nothing evaluated at an H score under 109, which is good. None of them think they're going to get there faster than 109 ticks. But some of them, they seem to think that they can still get there in 109 ticks, even if a thruster does not activate, even if the forward propulsion thruster does not activate on this tick. They can coast, and it'll still get there in time, the same amount of time, which is theoretically possible that a tick is not. Oh, except no, it's not. Okay, no, yeah, it is. I guess. Because if you're already going fast enough, accelerating further isn't necessarily that much better. So, maybe. But there's still some of them that are very clearly wrong. Like this one. It fires the reverse thruster, which does... It doesn't even reduce the number of... Well, it basically negates the current tick. So yeah, so we said at our last state, we thought it was going to take us 110 ticks to reach the goal. We fire the reverse thruster, and that's assuming we fire the thrusters optimally, essentially. And then here, if we fire the reverse thruster, it slows us down a little bit, and we're saying, okay, it's still going to take us 110 ticks to get there. And we're truncating the rounding. But also what's confusing is it's saying it's only going to take 109 thruster activations. Seems dumb. Why would it take fewer? This one that moves us laterally, yeah, okay, I kind of get that. That could be essentially rounding error. Ugh. Or not even error, just a result of the rounding. Okay. I'm gonna kill this execution. I'm going to run this again. I know I ended up stopping a round early, but I want to stop there again. So I know that the one after this is the one that definitely is having problems. From this set of neighbors that gets generated off of the one at 34 ticks, or 30, the one we're on 30, our 34th. It at least puts the right one at the top. But I'm curious to see if any of the others look weird. So, check that. Currently looking at 111, 111. This goes to 111, 110. So, Yeah, that is weird. $111,112. That I like. That seems right. 1111. That seems wrong. Yeah, anything involving the reverse thruster feels wrong. Like it's not. So that one's right. That is exactly what I would expect that one to be. I mean, the 111's like I kind of thought the 111 might become a 112, but 113 is right. Thrust up, thrust back result of that, but thrust down, thrust back is down 2 thruster activations. Why the hell would it do that? Alright, well that's fine. Let that be. Let's jump to our next state. This state is fine. Now I want to look. Step in is F11, right? I want to look at the generation of neighbors and see what happens. So this is a list of all the thruster combinations. Start with oh, with the, yeah, I see. It's the 1 thruster. It's 2 thrusters, yeah, okay. So this is starting with our 1 thruster, and this one is should be the reverse thruster. There we go, thrust back. So this is what happens when we fire the reverse thruster. Yeah, we get a nice vector with a lot of numbers that I have to assume is right. Yep. So, I mean, again, these should be essentially correct. I'm not totally sure what I'm looking for here. So the current state, the parent state, its velocity is mostly just positive x, slightly negative y, and slightly positive z. Our acceleration is negative x, slightly positive y, slightly negative z. That all makes sense. It's in the opposite direction of the direction the ship's currently flying, so that makes sense. So our resulting velocity should be, yeah, slightly less in x, more in y, and less in z. So we went from 3, actually, can I just state parent? Can I put these next to each other? I guess I could like pin them and put them next to each other. But... So 3126 becomes 3034. It's less. Negative 786 becomes negative 76. That is less negatives. That's positive change. 0066. 0064. that all makes sense. New velocity is probably correct. Plus, I mean, everything else has been calculating as expected. Right. Oh, yeah, and the length is not at max speed. So, our position is going to, I guess I should have left those open so I can compare. State dot, it's the parent position, position, -6779, -6266, that's less negative, so I mean, yeah, that's right. Still moving in the right direction. Negative is right. Less negative is, yeah. So yeah, so that all tracks. It's being essentially correct. Okay, so we have our new state. Now our command. Parent. Energy score is 3535. Our cost is going to be 1. Add 1 and 1. And our heuristic is what I want to look at. Because the heuristic. Oh, I have to step back out. Shift F11. I will just click it. Continue being notified when automatic step over happens. No, that's fine. Alright. In the heuristic. This is where I'm hoping you rubber duckies come in handy, because I'm going to explain this all to the best of my ability. I'm going to see if I can't find out why this comes out wonky. Because I would like to know. Alright. This is the distance that we still have to go. 7 meters in the X. Slightly negative Y, slightly positive Z. That's pretty much what we expect. That's a normalized unit vector version. That's fine. So, yep. So we look through all the thrusters and group them onto the axes. Just execute here. I don't need to step through those. Okay. So we have our 3 axis groups. Each has 2 thrusters. So we're going to look at one of the axes. I don't actually know which axis we're looking at the moment, but we'll see how this. I mean, this should tell us pretty quickly. Well, it should tell us whether or not we're on the one axis that we should have to travel along. this is actually the axis we want to be on. This is what we care about. Yep. Yeah, so our projected goal vector is the same as our actual goal vector. Yeah, same out to a lot of decimal places. There's rounding error for you. That x, at least as far as it's displaying, is actually identical. But you can see the really small y and z values. I mean, I guess they're not really, really small, but smaller. They start to differ in the last couple digits that are displayed. But yeah, the goal vector projected onto this axis is the same goal vector. So this is the axis we care about. Total distance to the goal, just over 7 meters. Our current velocity is gonna be the projected is gonna be the same because we're on the axis. Current speed is 3 meters per second. That's not gonna change. Projected goal velocity. Goal state. Oh, the goal velocity, right, the goal velocity is just 0. So, yeah, our target is 0. Okay. So we'll go through the 2 thrusters on this axis. One of them should be considered a gas thruster, not this one. Brake thruster, the other should be gas thruster. Acceleration, 5.5 meters per second squared. Brake acceleration, negative. So accelerating at 5.5 meters per second squared from the whatever we're going, 3 meters per second right now. We expect would take us 18 seconds to reach the 100 meter per second max velocity. And it would take us 905. Oh wow, that's a lot further than I thought. So I must not have been hitting that code. Different problem. Anyway, it takes us 905 meters to get up to our 100 meters per second with just a single ion thruster. And oh, there we go. And barely any more time. Wait, something's off here. Oh yeah, sure is. Sure is. So yeah, I noticed the time that it's supposed to take to reach maximum speed, and the time that it's supposed to take to go from maximum speed to our target speed of 0 are the same. And that's wrong. And that's because I'm using the wrong speed here. This is supposed to be the projected current speed. Yeah, That's gonna make a big difference. That could fucking do it. Yeah, I was always calculating the time it was gonna take to reach maximum speed. I mean, I guess that still doesn't really change anything though, does it? I mean, it definitely still could have broken me at higher. I don't know. I'm not sure that's the problem. That was definitely a problem. I'm not sure it really is the problem. Because all this is saying is that, yeah, it's basically always going to say, oh yeah, it's always going to take me 905 meters to reach max speed, no matter how fast I'm currently going, because it's always doing the calculation thinking I'm going 0, even though that's wrong. So, but I've never done any routes, at least not remotely successfully, in which I actually went 905 meters, or double that, because we would need the time to get there and then come back down. So this has never evaluated true, because the distance to the goal is only 7 meters. So this 1800 meters is definitely not less than 7. So that's never, yeah, that was definitely wrong, but I don't think it's the problem here. All right, so here we're saying, yeah, the ship doesn't have time to reach its max speed, so we need to find the point at which we need to reverse from accelerating to braking. And I believe I did this, I think this might have been my last stream, I don't know, one of the last couple streams. I was spent creating this function to calculate the velocity at that swap point by solving this system of equations. So yeah, let's see if this makes sense, because it probably does. So this is saying we expect to reach a maximum speed of 6.6 meters per second before we need to turn around and start braking. Not turn around, but start braking. Does that make sense logically? Our current speed is 3 meters per second. We've been going for 30 some ticks. We expect to go for 144 total, so we're expecting to go for 80, 70 in each direction. We're about halfway, so we should be roughly halfway to the swap point now, and we expect to reach 6.6 meters per second. Currently going 3. That seems reasonable to me. That's believable, and most of the calculations seem right, so that's fine. Seems believable. Oh, also, this is not with us going full power forward. This is with our most recent tick has been braking actually, so it slowed us down a little. So is that still right? I mean, it's not gonna change things that much. So yeah, probably right. So time to go from start to swap. From our current position to swap point is 0.6 seconds. We expect it to take us 1.2 seconds to go from the swap point to our goal. if we're halfway there, halfway to the swap point, and yeah, that works. So the total time remaining is about 1.8. Our current max time is 0, so our max time is 1.8. It says we're going to be accelerating for 38 steps and braking for 71. Ooh. Oh, yeah. Yeah, is this where things break down? I forgot I calculated those bits. It says we're accelerating for 38 seconds and braking for 71. That's 109 steps. So our total thruster activation count is 109. And so those are both floors. Seconds and step. Oh, technically this should be. Oh no, that is right. No, that's right. Like seconds and step and tick time are equal right now because we're doing 1 tick per step. But yeah, this is right because we always want the cost to be in. Oh no, we actually do always want the cost to be in ticks, not steps. So actually, that would be the correct thing to use. Right now it doesn't matter because it's the same number, but yeah, that's what that should be. So again, that didn't change anything in this execution, but that's where we get 109 for that. But this is going to evaluate to 110. 110.5. Oh, that's actually cool. Let's see. Yeah, 38.7 truncates down to 38. 71.76 truncates down to 71. But added together, because the time cost is the two added together, they became 110.5. So yeah, so it's rounding error. It's rounding error. Okay. I can deal with that. I can deal with that. So what I want to do is change the game here. I think this is good. I think calculating these steps is actually right. I'm actually inclined to believe that these are right. These are correct. Are they're not that they're more correct necessarily, but that they're more useful values. Maybe. Okay, gotta think through this a second. So what? All right, let me start typing out what I think I want to do, and we'll see if that. See if it works, if it makes sense. So I'm going to change this to an int and call it max ticks. And have a lot of extra echo statements in here that are commented out that are kind of difficult to read now. Max ticks should equal math.max of max ticks and steps accelerating plus steps braking. I think that's right. Well, oh, actually, oh no, yeah, that's right. So, yeah, if we say, yeah, we think we're gonna be accelerating for 38 seconds and then braking for 71. Then yeah, I'm gonna estimate that it's gonna be 109 ticks. That's fine. Even though those are both rounded up and probably, and yeah, even though they're both rounded up, realistically, it's probably 110. What we can't do, because it'll break the algorithm, is to overestimate the time that it's going to take. The heuristic always has to be optimistic. And 110 ticks isn't technically an overestimation though if it rounds up. If the sum of the two comes, yeah, it kind of seems like that might be right, but then we never found a goal when I did it that way. I might need to just test it this way, test it with this change and see if it works. See if it comes out any different. I mean, we definitely now should never see a thruster count that is less than our max ticks. Most of the time they're going to be equal because the because these are one step and all that are, I guess that, yeah, we're counting the number of times we activate thrusters per ticks, and then we're looking at the number of ticks it's going to take. And so if you move, up, down, right, or left and move along an extra axis, you're going to get a little bit of extra time or a little bit of extra thruster activations without adding extra time. Yeah, okay. Yeah, I want to run this. I want to run this and see what it looks like. Okay. I see. This slowed us down a little bit. Which is fair. fair. So right now we're looking at, yeah, 23.23 instead of 33.33. So because we tweaked things a little bit, some of the costs are coming out essentially more equal. But I think that's okay because it's the trade-off for not accidentally skipping ones that could actually be better. So this is fine. We'll take a look at 23 and see what it generates. So let's take a look at the neighbors. Oh. We go in reverse. And previously, our G-score is 24. And previously we estimated that it was going to take us 121 ticks to reach the goal. Now we're saying it's going to take us 122 ticks, which makes sense because we're gonna have to accelerate again. That's good. Yeah, that makes sense. Press down. Still going to take 121 ticks, but 122 thruster activations. That's fine. Yeah. Yep. 22. I kind of think it should be 23, but probably one of our floors is flooring to 0. So that's all right. Down and back. 22, 123. Yep, that tracks. Up, 121 and 124. Which is, okay, it's still weird that up and down get different numbers. That's still weird. So maybe I need to evaluate that. Why are thrust up and thrust down get different numbers? Because they should be the same. They should be exact mirrors of one another. You know what? That is assuming, though. Oh, I didn't think about that. That's assuming that every single command to this point has been a thrust front, which might not be true. It should be. Parent. Ooh. There was a thrust back in the mix. All right. Weird. I think I'm gonna have to scoot these a little bit. Only got a couple more parents to go. All right. So, interesting that, yeah, almost every single one of these in this path that we're taking so far has been a thrust front, but there was one thrust back command in the mix that evaluated as the same cost as the thrust front. And then probably the thrust front was never added to the frontier at all because, oh no, actually it should have been, because it should still have a different position, if slightly. and velocity. I mean, it's okay that these get evaluated sometimes, but it's weird that it would have made it this far. Another, what, 1, 2, 3, 4, another 4 notes deep after a reverse thrust. Like, that shouldn't still be great. 4 notes deep. Where we saw that there were 10 extra. Yeah, okay. I guess I could believe it. Except back should have been the worst of them. Except that back should have been the worst. Yeah, now I'm starting to wonder if evaluating these times as ticks is a mistake. I thought it made sense. I really did. I really thought it made sense, because the idea is that it eliminates the variance in it eliminates the variance caused by rounding error when you, for example, do your forward thruster and then forward, right, and left all together. Okay, you know what? There was an identifiable problem in the fact that the up and down commands resulted in different results. But you know what? There's another problem, and that's that it's getting late. I really want to solve this, but I think I may have a better shot at doing so successfully tomorrow or another day. I'm not going to promise that I'm going to be back tomorrow, but I'll try, because I'm going to want to fix this. I'm going to want to find this. But, things happen. I have a 1-year-old. So, yeah, I'm going to write down that the next thing I want to solve is why up and down commands result in different numbers of thrusters that are expected to be activated on the heuristic. Okay. Next streams. Add me page. What's today? Today's 18th. So my notes from the 18th. The next stream, I want to find out why thrust up or down result in different thruster counts on the heuristic calculation. Because I know, like, we saw that those were weirdly different, and yeah, because thrusting down resulted in a heuristic of only requiring 122 thrusters to reach the goal, and thrusting up guessed that it was going to be 124, and those should be exact mirror images of one another, and it's really weird that they were off by 2 thruster counts. So I want to find out why that is, and I want to explore that next time. Yeah, I think that'll be a really good place to pick up, because if we can find out why that's wrong, it's entirely possible that that's causing just enough other weirdness in other parts of the code that it fixes other problems too. So that's what I want to do. All right, we can stop this debugging. But that looks great. All right. Well then, thank you for coming to see me. If you are just as interested as I am in seeing the conclusion of this one, feel free to follow and I'll let you know when I pick it up. Hopefully it's tomorrow night, but like I said, you never really know. Yeah, and I mean, obviously, if you want to see me do more stuff in general, that's great. But regardless, thank you for being my rubber duckies tonight. It really is. It's helpful to me to talk through these things out loud. So appreciate it. Yeah. So guess that's my plan for next time. Yeah, I'm gonna go to sleep. I work tomorrow. So I hope you all have yourselves a good long rest, and I hope you recover all of your spell slots. Good night, everyone.